Volker Bach from Braunschweig. Sorry, let me check this. Okay, so Volker Bach is going to talk about sharp and smooth Feshbach-Schur map. Please go on.
Yeah, thank you very much, Luis, and thanks for coming to this conference. It's a great conference. It's for me a great honor that this is celebrating my 60th birthday. Let me thank the main organizer of this conference, Miguel Ballesteros, on this occasion once again, and then also the team that has now assembled here, which helped in the past year to organize this conference. There's Luis, there's Ivan, there's Julien was here, maybe he has left for a minute, and other organizers and the staff. I'm very grateful to UNAM that this is now set here and takes place. Ucero is here, thank you very much. So I appreciate that, and I'm glad that I also scientifically can contribute a little bit. I will say in the end a few words about the collaboration of my university, TU Braunschweig, and UNAM that we have worked on. Miguel mentioned this before for the past years, and the time we invested in that is at least as much as what we invested in the mathematics we did together. Well, let me come, however, now to the scientific part, the sharp and smooth Feshbach-Schur map. I take this talk here as an occasion to present to you a review on a method, much more a method than, so to say, the actual application of this method. And this method has been of key importance for the analysis of problems in quantum field theory that were studied in a field of theoretical physics, which is known as non-relativistic quantum electrodynamics, which is a kind of a contradiction in itself. But let me not go into this now. Let me rather go into the mathematical description. So here's the program. We start with a sharp Feshbach-Schur map. I will introduce this to you, and you will see that you are familiar with it actually. And then I come to its application in physics of a more advanced kind. There will be a renormalization group and normal ordering that plays an important role. And then hopefully it will become visible that there is a need to change the sharp Feshbach-Schur map into something more regular. And this is the point when I come to the third item, the smooth Feshbach-Schur map comes about. And then as a final point, I will get into what we call the continuous renormalization group. I will explain what this is when we are there. Let's start. So Feshbach and Schur, those names were just dropped, and this refers to two methods that were found, I would say, independently. In fact, there are the method is reinvented or refound often in different contexts. So on the mathematical side, there was Schur who introduced what is called the Schur complement. Let me first, however, describe the method. So we assume we have a problem on a complex and a separable Hilbert space H, and then we have a Hamiltonian operator, also called H, whose spectrum we are interested in, and we analyze it by means of a suitably chosen projection P. and its complement projection P bar. So these are assumed to be bounded operators, and their ranges are called HP and HP bar. Let me make a remark here. Yeah, let me remark that P bar is the P perp, the perpendicular projection, in case that P is self-adjoint. But in the applications, which I cannot go into in detail, it's very important that we can also allow for non-self-adjoint projections. And so keeping P bar here is not just an academic possibility that may occur, but we actually need to be more general and allow for other than orthogonal projections. Anyway, let me come to the basic fact about these projections, Hilbert space and H. If we know that the restriction of the Hamiltonian operator H to the range of P bar is bounded invertible, then the sharp Feschbach-Schur map, which is what is called the Schur complement actually. So this operator here, which acts on the range of the projection, so smaller Hilbert space, but a more complicated operator, this is isospectral to the original Hamiltonian H in the following sense, that the dimension of the kernel of H equals the dimension of the kernel of the sharp Feschbach-Schur map. So that means if H is invertible, then so is the sharp Feschbach-Schur map of H, because then the kernel is just trivial, has dimension 0. And if it's not invertible, then we have eigenvalues, and in fact the multiplicities, the multiplicity is conserved since the dimension counts then the multiplicity of the eigenvalue. So this operator, if we have in addition a parameter z introduced here, that's the Schur complement, and that was introduced by Schur in 1917, so it's fairly old. And however, it was, so to say, rediscovered by physicist Hermann Feschbach, and much later in 1952, when he found that one can actually formulate perturbation theory in theoretical physics of isolated eigenvalues, can formulate this systematically by means of the sharp Feschbach-Schur map. And this is elementary, I know, but let me go through this with you anyway, because the strategy will appear later again in a more complicated context. So now I want to study a concrete Hamiltonian, namely a perturbative problem. So I assume I have a sum of a piece of a Hamiltonian H0, whose spectral properties are to me completely known. And then I have a perturbation W, which is coupled in by some coupling constant G, which is a small number. And here, for simplicity, I assume that the operators are bounded. H0 is self-adjoint, and so is W. And W has, say, a norm bounded by 1. So when G is small, then the perturbation is small, and I can tune its strength by making G smaller. All right, so now I assume that E0 is a simple eigenvalue of the unperturbed Hamiltonian, and with a normalized eigenvector psi 0, and that the other parts, eigenvalues or other parts of the spectrum of the unperturbed operator is away at least by a distance of 1 from E0. Then if I apply theorem 1. So I can apply theorem 1. I need to check the invertibility of H0. So first of all, I should say, what is the P here? P is the projection onto this normalized eigenvector psi 0. And so the resolvent, the H0 is invertible on the orthogonal complement, and the resolvent has in fact norm 1. And so if we perturb it by an operator of small norm like the W, this does not change. So the assumption of for an application of theorem 1 is fulfilled. And we obtain that EG is an eigenvalue, is in the spectrum of HG if and only if the dimension of the kernel of the Sharp-Feshbach Schur map is at least 1. And in fact, since P is a one-dimensional projection, it will be exactly equal to 1. So we will have automatically also a statement about the multiplicity of the eigenvalue EG that we find. So, but then since the projection P we use here is one-dimensional, this statement here that the kernel has at least a dimension 1 directly transcribes into a statement about a vanishing of a matrix element of the Hamiltonian, yeah? The Sharp-Feshbach Schur map, that is. So here it is. This is the Sharp-Feshbach Schur map sandwiched with an unperturbed eigenvector psi 0. And now we can work out all the matrix elements in this expression here in the middle. There's a curly brace missing here on the right. We can work out the matrix elements and solve for the number EG, and we get an equation for EG. EG is equal to E0 plus the first perturbation theory first order correction, the usual one, is of order G, minus G squared, the second order perturbation correction, and then the powers of G3, etc. There's one thing I'm brushing here under the rock, which I want to draw your attention to. This is an implicit equation for EG, because on the right side, the perturbed eigenvalue appears here in these resolvents. So one actually is not finished at this point and to determine EG, but you have to systematically now move this EG here by solving a series, by doing a series expansion, move it over to the other side of the equation here. And so one gets a slightly more complicated series. But this can be done systematically, and this is well known how to do it. So let me not go into it. So this is just to illustrate that this is a method to analyze the spectrum in case of isolated eigenvalues of finite multiplicity. Here, multiplicity 1, and that was the origin of the method in theoretical physics in 1952, found by Feshbach. All right, so now I want to move on to more advanced applications. And the one I'm interested in is from quantum field theory, and I illustrate the application on the model which is called the spin boson model. The spin boson model is an important model in quantum optics, but it has the for me today it has the advantage that its structure is simple, and I can, so to say, get my point across to you, the audience, in an easier and hopefully more comprehensible way. So let me just go through the model assumptions. The Hilbert space in this case is the C2 times the Fock space of the photons. Now, you don't really need to know what a Fock space is, but let me write down what it is for completeness anyway. It's a direct sum, orthogonal sum of the n photon sectors, f photon n. And here the 0 photon sector is a one-dimensional space spanned by the vacuum vector, capital omega. And then there is an n photon Hilbert space, n being any natural number, not following the French convention, any natural number, and then we have the n-fold tensor product of L2 of R3 and then symmetrized wave functions. It will not play a big role what this precisely is in the talk, so don't worry. The unperturbed Hamiltonian, H0, we have seen that this is an important object for the analysis. That's a 2x2 matrix, a two-level atom in the physics context, with E0 being the smaller number, the ground state energy of the atom, and E0 prime, the excited energy of the atom. So this is actually not just a caricature, but this is realized in optical traps where experimental physicists try to model a quantum computer with it, with these 2x2 matrices, basically. Okay, so then there's another piece in the the unperturbed Hamiltonian, that's the photon energy operator, H photon. And the photon energy is, using physics language, is the second quantization of the single photon dispersion relation. But let me be more specific. The photon energy operator here acts, photon Hamiltonian acts on the vacuum vector by sending it to 0. So the vacuum vector is just mapped to 0 by the photon energy, and the any n photon wave function with is at momentum k1 to kn is multiplied by the sum of the photon energies, omega of k1 up to omega of kn, to the wave function. So it's actually a Fourier multiplier. And since the photon dispersion relation is k absolute value, one could say it's the natural action of the square root of the Laplace operator on vectors with n momentum entries. So, so let me just conclude from here. The photon energy operator has a positive spectrum, purely absolutely continuous above 0, and then an eigenvector at 0. So the spectrum of the photon operator looks like this. We have here, here's 0. This is an eigenvalue. And then we have continuous spectrum above 0. So now let me move on. Well, maybe I want to go back for a minute. Let me go on and describe the spectrum of H0. We have the spectrum of the 2x2 matrix E0 prime and E0. This is, of course, just two eigenvalues at E0 and E0 prime. And the distance between these eigenvalues is 1 or more. And then when we look at the spectrum of the Hamiltonian, unperturbed Hamiltonian, then it consists of two parts. There's the energy at E0 and E at E0 zero prime again, and then we get two continuum branches emerging from these 2 points. So the spectrum is the half line to the right from E0. And this is the picture going with it. Now, I do not want to specify the interaction in this talk here, the W, that we want to treat as a perturbations. It's not really so important, so I rather leave it out. It would cost too much time. But let me say that the assumption I made for the first example, that it is a bounded perturbation, is not correct. It's not bounded, but it's small in sense of relative boundedness, namely it's an infinitesimal perturbation of the unperturbed Hamiltonian. So now we come to the basic questions that we are interested in. The question A concerns this value E0 here. This E0 is for the in the unperturbed situation is an eigenvalue at the bottom of the continuous spectrum. And E0 prime is an embedded eigenvalue, embedded in the continuous spectrum. And then naturally, the possibility is plausible that if we couple in a perturbation, then no matter how small the coupling constant is, these eigenvalues will disappear. Because it's unstable under perturbations. And we wonder, does this occur in this situation? So is the picture when we have when we want to draw it for G coupling constant non-zero, the whole spectrum is shifted a little. So we have here maybe an EG, and then one can also see that it will be essential spectrum just above EG. But the question is here an eigenvalue? And then what happens to E0? I mean, are there here traces of resonances? Yeah, resonance. Let me just write this and put a question mark. So, so these are important questions for physics. For the physical interpretation of the model. And I will only address the first question, namely about the ground state A, but only because it's simpler to explain. Resonances, I think, so what happens to the excited atomic energy when we switch on a perturbation is mathematically more interesting, is more rich, certainly. I mean, more complex, and physically perhaps even also more important. So let me just say one word about the resonance case. If we want to say something about a resonance, the resonance will actually be a pole of the resolvent of EHG in the lower half plane. And if we want to uncover this pole, we need to use complex deformations. So we need to use some non-trivial tools from complex analysis and analytic families of operators. All this is a lot of framework that I don't want to introduce in this talk. But let me just mention that it leads to studying spectral properties of non-self-adjoint operators, and that is much more difficult because we know we have much less many tools available for the study of non-self-adjoint operators. And then also the physical implications about the time decay of wave functions one obtains from the study of resonance are of a relatively weak nature. So let me not go into this. But I want to mention that there are important results obtained on the theory of resonances. Starting from 1908, there is a series, different groups have worked on this statement here. And let me point out that Israel Siegel, who will talk this afternoon at this conference, was the first to construct resonances and prove their existence in the case of what we would consider the fully interacting model. And then there have been other approaches and improvements, also studying the full model for minimally coupled electrons in atoms by Ballesteros, Pizzo, and myself, and by Ballesteros, Pizzo, Iniesta, and myself in more recently in 2017 and 2021. So if you're interested in these works, I'm happy to give you references in more detail. Let me come back to the spin boson model where we were interested. Maybe I just go back one more time. What was it here? I had this unperturbed Hamiltonian I wanted to study. Now I address the question of what if we perturb this operator. So to study this, we introduce the projection onto the excited states, P up arrow, and onto the ground state, P down arrow. And then we apply the Feshbach-Schur map, the sharp Feshbach-Schur map, with a projection, P down arrow times the projection onto photon energies which are smaller than 1. And so what this projection does, let me just point this out, is we project onto this eigenvalue and then only on the part of the continuous spectrum which is only, say, 1 away. So here is E0 plus 1. Yeah? So we cut out this part and the projection projects only on this part of the spectrum. And then in turn the orthogonal projection, the P bar corresponding to it, is deals with energies that are bigger than E0 plus 1. So here is the range of P perp. I indicated it here. And since we're interested in the spectral properties of that point, it means that we have regularized this problem by choosing this projection. Namely, we got rid of all the energies that are at least a distance 1 away from the point we're interested in. Okay, so then here's a little computation that for lack of time I will not go through with you, but we can actually now in a fairly simple way see that the full operator, the perturbed operator, H naught plus the perturbation minus the ground state energy E0 minus an energy difference that we want to choose, so we want to tune so that it gives the difference of E0 to the full energy. So if we restrict this to the range of P perp, then a series of quadratic form estimates show that this operator is positive and bounded away from 0 by a factor 1/2. So it's bounded below by 1/2 times P perp. So therefore it's perfectly invertible on the range of P perp. And we can apply the isospectrality theorem. And then what this tells us is that the number E0 plus Zg, so that would be Eg, is an eigenvalue, a point in the spectrum of the full Hamiltonian, hopefully an eigenvalue, if and only if the kernel of the corresponding Sharp-Feshbach-Schur map of this operator is non-trivial. And here, this Feshbach-Schur map operator, I took only the part of it which acts on the Fock space. The part that acts on the atom is now trivial because this is a one-dimensional projection. So I have here an operator which looks like this Sharp-Feshbach-Schur map, and then tracing out the projection onto the lower right corner. Okay, so what we have gained so far is we have transcribed the original spectral problem into one which is now encoded in the Sharp-Feshbach-Schur map. And now we come to the idea of the renormalization group. The idea of the renormalization group is now to iterate the application of the Feshbach-Schur map. So let me just indicate how this goes. We choose a small parameter rho, a small fixed number. Let's say it's smaller than 1/32. So then powers of rho, positive powers of rho, rapidly converge to 0. And we introduce these projections Pn, which project on photon energies less than rho to the n. So if we look here in this picture on the range of these projections, so let me just enlarge this picture here. Here was E0, and I had this first projection here. The stuff has gone away now, and we are here in the range of P0, the 0th projection for rho to the 0, which is 1. And then the idea is that we analyze the spectral problem here, the Sharp-Feshbach-Schur map. We get an energy shift, a small energy shift that brings us here to another point, which is then Eg2. So E0 would be the position of the ground state energy to zeroth precision, and then we get a correction of the energy to precision 1, and then we focus this on a smaller ball by means of the projection P1. So then photon energies of size rho only are retained. And then we have a new spectral problem to study. We get another energy correction. Let's say it moves further to the right here. So this number is then Eg2, and we project onto P2. So now I mess up this picture, but I think you get the idea that we get on ever smaller energy balls. They're not concentric. They move a little bit depending on how the energy correction results from the previous step. Of course, you can imagine this is fairly complicated to write down, and I'm not going to do it, but it can be done systematically, and it leads to a chain of spectral problems. So we have the original Hamiltonian, then we get, here it is, Hg minus E0 minus E, and we know that by the isospectrality, its kernel has the same dimension as the one of this H0, this first application of the Sharp-Feshbach-Schur map. And the range of the spectral problem is reduced from the original Hilbert space to the range of P0. So that's a big reduction. And then we make H0 be the argument of the next application of the Sharp-Feshbach-Schur map, get an operator H1, and the isospectrality guarantees that we don't lose, so to say, predictive power over whether this is an eigenvalue or not, the number we are looking at. And we proceed in this vein and get a sequence of Hamiltonians which converge in a suitable sense. Namely, there is a normal ordering procedure that yields these energy corrections that I have not described. So adjusts the energy offset and guarantees that the interaction, the resulting interaction, so we start with the interaction W, and then we get an effective interaction W super 1 after the first application of the Sharp-Feshbach-Schur map. And its norm in a suitable relative bound is much smaller than the one of the original interaction. And then in the next step, this gets reduced even more. So for the interaction, the second step, and so forth. And the convergence of the renormalization scheme basically is guaranteed by the observation that this decreasing of the interaction strength is faster than the shrinking of the radii here of these balls. But there is a problem that arises here. Namely, the normal ordering procedure that I have not described, but I just mentioned here, that makes it necessary to take derivatives of this projection, the characteristic function of photon energies less than 1, and derivatives with respect to the operator. So that's an object that is not really well defined. So if you take the derivative of the characteristic function, there is, in some weak sense, it's a delta function, h photon of delta h photon minus 1. But then what is this delta function here, distribution? It's not easy to make sense of it. So one has to be very careful when one carries out estimates in this framework. And this leads to technically rather involved constructions. So in the original work where this framework was introduced, and also in the work of Ballesteros, Fröhlich, and myself from 2015, where this was used to set up the continuous renormalization group version. I'll come to that later. So, so therefore, it was some progress that the smooth Feshbach-Schur map was found, the smooth Feshbach-Schur map, as opposed to the sharp. So let me, so to say, start all over and introduce to you the smooth Feshbach-Schur map. The setup is very similar. We have a complex Hilbert space. We have a Hamiltonian we want to study. But the projections are now replaced by what could be called an IMS partition of unity. So we have two operators chi and chi bar, whose squares add up to 1. These are positive operators between 0 and 1, so they are self-adjoint. And we have an operator t, which could be thought of as a free operator, which commutes with chi and chi bar. And then we define the interaction W to be the difference between the spectral problem we want to analyze, H, and the operator T that we are freely choosing, so to say. Then there is an isospectrality theorem, which says that under the similar invertibility condition on the range of the so to say, orthogonal projection, chi bar. Under this, the smooth Feshbach-Schur map is isospectral to the original Hamiltonian. Namely, the dimension of their kernel are the same. And the smooth Feshbach-Schur map looks much like the sharp Feshbach-Schur maps. There are, if you look into it in detail, there are differences, but let me not go into this. This is a definition. And so this theorem was established by Chen, Fröhlich-Siegel, and myself in 2003. And we use it in the following way for the spectral problem of the spin boson model. We use it in the following way. We choose instead of choosing the characteristic function, let me go into here, instead of using the characteristic function of photon energies less than 1, we use just a smooth function which is scaled appropriately by rho, powers of rho to the n. So the function chi that is mentioned here, chi looks like this. I just draw a picture. So it's a smooth characteristic function of the interval 0 to 1. It's the usual thing you use in PDE theory. So it has, it yields the same properties, the same chain of identities, of dimensions of the kernel, and normal ordering procedure is also taken into account here. Again, the normal ordering procedure guarantees that the interactions that are obtained at each intermediate step are dramatically reduced in norm. And the big advantage is that now this problem of taking the derivative of a characteristic function is solved, because here we now only take derivatives of smooth functions and we get some explicit, nicely differentiable function out. So this smooth Feshbach-Schur map produces at least the same result as the sharp Feshbach-Schur map, but the framework is much simpler. And this is the method that is used basically nowadays when Feshbach-Schur maps are used. So now finally I want to come to the continuous renormalization group. The point here is to replace the iterations by going from chi n to chi n plus 1 to reduce the scales in discrete iterations to do it in a continuous vein. So that is to scale the cutoff energies by e to the alpha and let alpha just be a continuous parameter that tends to infinity. So then the idea was that we want to have a differential equation rather than an iteration of operators. This would simplify the equations to study dramatically. So in this paper of Ballesteros, Fröhlich and myself in 2015, we obtained a continuous renormalization group based on the sharp Feshbach-Schur map, but we did not get a differential equation. So this was a big step forward, but the differential equation was not yet established. But let me, and it's still not, but let me report on a recent progress, namely in a joint work with Miguel Ballesteros and Jakob Geisler, a graduate student of ours. We obtained a continuous renormalization group based on the smooth Feshbach-Schur map. I don't know why I omitted the Schur here. So the role of this operator T in the smooth Feshbach-Schur map is now characterized and kind of demystified in the paper. And the flow property is established of the renormalization group map, but still we do not have derived the differential equation. There are more things to do on that way. And moreover, it's fairly clear that one obtains the sharp Feshbach-Schur map from the smooth Feshbach-Schur map simply by choosing chi to be a projection. But in this new paper, we also show that the converse is also true. One also obtains the smooth Feshbach-Schur map from the sharp Feshbach-Schur map on a slightly bigger space. So at this point, I would just want to emphasize that Miguel Ballesteros and I, we have a long-term collaboration since 16 years now, in which these works that I have mentioned during my talk have been produced and we studied. And Jakob Geisler, although he's not formally speaking a student in the double degree program, is a prime example of a graduate student that is trained and advised by both Miguel and I. So we have a kind of a structured way of training the doctoral students, and you can see from this this transparency that it has some success. And there are more students that follow this path and are now on track of the double degree program. Let me mention Merten Mlináček. He was here until May for 10 months at UNAM, and has done here very good work with Miguel together. So he's now back in Braunschweig. And in October, Pedro Guyen, who is here in the audience, will come to Braunschweig. He's a graduate here of UNAM and comes to Braunschweig and be there for a year and, so to say, the third graduate student in this joint program of joint advising. And so at this point, I would like to encourage the colleagues here from UNAM to take advantage of this double degree program. It's a structure, a legal structure that now, after having sorted out all the paragraphs and stuff, to easily start cooperations with the math department or other departments at TU Braunschweig and have joint PhDs. I'm sure that both parties benefit a lot from that. With this, I close, and I thank you for your attention.
Are there any questions?
Yeah, I have a simple question. So you speak about the differential equation. On which space you are speaking?
Yeah. So this would be a differential equation on the space of operators. And this is in fact in the spirit that Wilson originally had. So you would have a space of Hamiltonians parametrized by interaction coefficients, and then the flow would be on that space. It's one could also say, this is not the only renormalization group framework, as you certainly know, but let me mention it anyway. There's also renormalization group formulated in terms of renormalization of Schwinger functions. That's done, for example, by Manfred Salmhofer, who could not come, unfortunately, to this conference. And there, the Schwinger functions, which characterize completely the system, are renormalized and flow. They also have continuous setups.
Are there more questions?
Thanks for the talk. So when you go back a few slides, so when you say much smaller, you mean in terms of rho? So it's an expansion in rho? Or? No, yeah.
This one or
the one later?
One later. Mm-hmm.
So the much smaller, it's to be understood in terms of rho. Or I mean, what are the parameters here?
Yes, I mean, it has to be much smaller compared to rho. So you see that, I mean, it's not exactly what you, how you would formulate it, but you see that I change here the scale. So this is photon energy plus 1, and this is photon energy plus rho. And
Yeah.
so the appropriate cutoff at that point, at that stage. And this should be, so the typical photon energy would be of order rho, and then so this number, so that's already divided out here, so to say. Yeah, I put a 1 over rho inside, so this should be much less than 1, what I have here. And it turns out that actually it will be of order. I mean, this second line will be of order rho to some positive power less than what you had in the previous line. So you get an improvement, which is, I mean, a more rapid convergence to 0 of the interaction norm bound than your energy scales shrink.
Thank you, Volker, for your nice and very interesting talk. I have 2 questions. One of them is, what happens when your original eigenvalues, E naught and E naught prime, have a finite multiplicity? Can you follow the path of the situation that you have after you introduce the perturbation?
Yes and no. Very good question. It becomes more difficult, and let me say, it's not really worked out, but, or only partially. But the idea is that, let's say you would have here a twofold degenerate eigenvalue, a twofold degenerate unperturbed eigenvalue instead of just a simple eigenvalue. Then the normal ordering procedure that gives the new Hamiltonian will hopefully break up split the eigenvalue into 2. Yeah, that would then be followed separately in further steps. But if it's not broken up after the first iteration, you would have to hope that at the second step it will be lifted, the degeneracy, or at the third or at the fourth. And it becomes, however, more and more complicated step by step. The operators involved there are also then, I mean, their structure are complicated to follow. So it's not really been worked out. I mean, originally it was thought that this is a kind of a trivial extension of the problem, but I actually think that it's worth looking into. It's not so easy. So some part of it has been proved that the degeneracy does lift. Last week we heard in Merida a talk by David Hassler where he reported that they have results on certain models were then in second order perturbation theory. So after 2 steps, the degeneracy is lifted and then one has simple eigenvalues only.
Yeah, thank you very much. My second question is about this double program that you have announced. What are the universities from Germany involved in this program so far?
This is a bilateral program between Braunschweig and UNAM, the one I was talking about. However, there are other universities who have also made contracts with UNAM. For example, there's the University of Erlangen, which also has such a contract. And there are, I believe, I mean, this the UNAM people know, I believe there are more in the pipeline, so to say. There is I mean, UNAM has an office in Berlin where there's permanently somebody there who acts as a ambassador of UNAM in Germany, and so that is very useful to make a touch between UNAM and German universities. Let me add another comment. I think that it's easy now to get new contracts because the German universities have a common guideline to sign contracts with foreign universities. So in some sense, our contract was a breakthrough because we follow the general guidelines of German universities, and so other universities can now just take our contract as a blueprint.
Thank you.
Any more questions?
Yes, I have a question that is a little bit speculative, but I was wondering, there's a version of the renormalization theory that you're subtracting things like the first moment, the total energy from a partial differential equation to solve it. And there's more organized algorithms like your BPHC, or we learned last week about another algorithm that's only for the linear case. And is this comparable to those other renormalization schemes?
Yes and no. I mean, it's comparable in the sense that you think of it as a dynamical system. You're in the space of operators, what you want to study in this chain of operators. And then there are relevant directions, marginal directions, and irrelevant directions, and to use the dynamical system language. And hopefully there are only, in our case, we have only one relevant direction, which is the energy. But fortunately, we can take this relevant direction explicitly out of the problem at every step. So we can adjust it to be zero. And then marginal directions don't appear. And the interaction is infinite dimensional. Yeah, so to say, infinitely many directions, but they're all irrelevant. So which is what is indicated here, though. So they fade out, they decay away, and in the end, they don't become, they're irrelevant. Yeah, so in this sense, this is the same. Yeah, you want to go to an effective theory, subtract numbers so that you get a new problem which is tractable and does not explode, and then try to repeat this procedure.
Okay, so are there more questions? Yes. Please go ahead.
Okay. In the micro-local community, people would often talk about the Grushin method instead of the Feshbach method. Are they really the same? Just
Yes.
They are. Okay.
Yeah. I could write down a dictionary. One can do it. I mean, there are other, like, I think Lyapunov-Schmidt method is also the same as this.
Thank you. Are there more questions? No? So let's thank again the speaker.
Thank you.